A takeout food container. The foam insert protecting a brand new television. Polystyrene foam is everywhere, yet more than 95% of its volume is nothing but air. In the United States alone, an estimated 1,500 tons of polystyrene end up in landfills every single day, while less than 1% is recycled. The reason is simple. Foam is too light to be valuable, yet too bulky to transport economically. But inside a small workshop in Mexico City, that same discarded foam is getting a second life, transformed into something few would ever expect: picture frames. But how can they compress a mountain of foam that is almost entirely air, turn it back into solid plastic, and then transform it into brand new picture frames? To answer that question, we first need to understand what this material really is. The name Styrofoam, which many people use to describe all foam packaging, is actually a registered trademark introduced by Dow Chemical in 1947 and now owned by DuPont. It refers only to a type of rigid insulation used in construction. The foam cups, takeout containers, and protective packaging we see every day are technically called expanded polystyrene, or EPS. EPS became one of the world's most widely used packaging materials for a reason. It's incredibly lightweight, an excellent insulator, remarkably good at absorbing impacts, and inexpensive to produce. But the very structure that gives it those advantages, millions of tiny air-filled cells making up almost all of its volume, also makes it one of the recycling industry's biggest challenges. That was exactly what Hector Ortiz noticed while he was still a university student. He watched waste collectors eagerly buying aluminum cans, plastic bottles, and cardboard, yet they always ignored foam packaging. Not because it couldn't be recycled, but because nobody was willing to pay for it. That observation led to a simple question. What if this overlooked waste could become a source of income instead? Hector Ortiz and his team operate with a surprisingly simple business model. Companies pay Renueva to handle their polystyrene waste, while residents can drop off their own foam at the facility. The company also organizes regular collection drives at schools and local communities to expand its supply of recyclable material. But the biggest challenge appears the moment the first pieces of foam are loaded onto a truck. A trailer filled with loose EPS quickly runs out of space long before it reaches its weight limit. In other words, companies are paying to transport mostly air. As a result, transporting untreated foam can cost several times more than hauling other materials of the same volume, sometimes even exceeding the cost of simply sending it to a landfill. For many recycling businesses, the economics fall apart before the material even reaches the factory. That's why, before Renueva can recycle polystyrene, it has to solve a seemingly simpler problem. How do you make millions of tiny air pockets disappear? Simply throwing a bulky block of foam into a melting furnace would be incredibly inefficient. Most of the energy would be wasted heating the air trapped inside, rather than the thin layers of plastic surrounding each tiny bubble. Mechanical shredding alone doesn't solve the problem either. While it breaks the foam into smaller pieces, it typically reduces the volume by only about 10 times, still nowhere near enough to make transportation economically viable. That's why modern recycling facilities combine heat and pressure in a single process. By forcing the trapped air out while softening the plastic, they can shrink the material far beyond what mechanical grinding alone could ever achieve, turning a logistics nightmare into something practical to transport and recycle. The process begins by shredding the foam into small flakes, making it much easier to feed into the recycling equipment than leaving it in its original bulky form. The shredded material is then fed into a machine that combines heat and high pressure. As the temperature rises and pressure builds, the polystyrene softens and is pushed through an extruder, emerging as long, continuous strands that look remarkably like freshly made spaghetti. These strands pass through a cooling bath, where they quickly harden before they can bend or deform. Finally, rotating blades chop them into uniform pellets, about the size of grains of rice, ready to be bagged and shipped to manufacturers. The entire operation runs almost continuously. Foam scraps go into one end of the machine, and just minutes later, finished plastic pellets come out the other. Using this process, Hector and his team recycle around 16 metric tons of polystyrene every week. The result is remarkable. The material's volume can be reduced by as much as 90 times. In other words, 90 bulky bags of foam that once filled an entire warehouse can be transformed into just a single bag of plastic pellets. Renueva's work doesn't end with plastic pellets. The company sells them to Marcos y Marcos, a picture frame manufacturer capable of processing around 6 metric tons of raw material per day. There, the recycled pellets are melted once again, injected into molds, and assembled into the final product, picture frames. Even old picture frames, after years of use, can return to the very same production line to be recycled into new plastic pellets. It's a practical example of the circular economy, where today's finished product can become tomorrow's raw material. That doesn't mean polystyrene is free from controversy, however. In 2019, the International Agency for Research on Cancer, IARC, classified styrene, the chemical used to produce polystyrene, as Group 2A, probably carcinogenic to humans. It's important to understand that this concern is not about finished, stable polystyrene products themselves. The primary risk is associated with exposure to styrene monomer, particularly in manufacturing environments where workers may inhale chemical vapors or airborne particles over long periods. For ordinary consumers, the estimated level of risk is considered significantly lower. But if this model works so well, why has it been adopted in so few places around the world? The answer takes us back to the same problem introduced at the beginning of this story. Most of what those trucks are transporting is still air. Polystyrene foam takes up an enormous amount of space while carrying very little material value, making it far cheaper for many cities to send it to landfills than to invest in the infrastructure needed to compact and recycle it. Many governments have chosen a completely different approach, banning single-use foam instead of trying to recycle it. The European Union prohibited expanded polystyrene food containers in 2021, followed by Canada in 2022. In the United States, however, some states have taken another path by requiring manufacturers to help pay for the collection and recycling of the products they sell. According to an analysis by the Recycling Partnership, states with these policies have reported recycling rates that are roughly 3 times higher than those without them. In other words, the obstacle has never been whether polystyrene can be recycled. The technology has existed for years. What's still missing in much of the world is an economic incentive strong enough to make recycling a better business decision than simply burying the material in a landfill. While most recycling facilities are still struggling with the challenges of collecting and transporting foam, A different solution is beginning to emerge in Canada. Instead of shredding and melting polystyrene with heat, a company based in Montreal dissolves the foam using a selective solvent at room temperature. As the polystyrene dissolves, the foam's structure virtually disappears, making it much easier to separate and remove contaminants such as food residue, labels, adhesives, and other additives. The biggest advantage of this process is its ability to recycle heavily contaminated foam, material that conventional heat compaction systems would often reject. The company's first commercial facility was designed to process around 9,000 metric tons of polystyrene each year, equivalent to roughly 15% of the polystyrene sent to landfills annually in the province of Quebec. The technology is still in its early days. It requires substantial upfront investment and is unlikely to replace conventional heat compaction systems anytime soon. Perhaps the future of polystyrene recycling won't belong to a single breakthrough. Instead, different technologies may each solve a different piece of the puzzle. And the race to find a solution that is not only technically effective, but also economically sustainable is still far from over. At a market somewhere in Mexico City, food vendors continue packing meals into foam containers every day for one simple reason. They're cheaper than almost any alternative. A ban alone doesn't make that demand disappear if there isn't an economically viable replacement. That's also what Hector believes. In his view, no environmental solution can survive for long unless it creates economic value alongside environmental benefits. If even a material once dismissed as worthless can find its way back into the manufacturing cycle, then perhaps the real question is no longer whether the technology to recycle it exists. The real question is, how many other types of waste are still waiting for someone to discover the value hidden inside them?